I want to do some rigid bodywork examples. These are a set of examples I think are kind of useful, and they deal with some of the concepts in the course. Start out with some problems looking at rolling, and then go into kinematics and some kinetic analysis. Again, the whole idea is that this course combines a group of ideas to put together a package of approaches to solve problems. So let's consider this case. We have what's the final speed of the slider? That's slider's A. And if the system starts at a theta, which is down here, of 72 degrees. So if you have 72 degrees here, and you know that this is going to be here, you're going to have two types of motion. One, you'll have translational motion here as the slider moves down. You'll have translational motion of the center of gravity, or the center of mass of the wheel. You'll have general plane motion associated with this rod right here. And finally, you'll have wheel rotation and translation simultaneously. You'll notice here I've been good. I've put down my axes, x to the right, y up, and positive moment counterclockwise. I also know right away that I have an instantaneous center of zero velocity that is in contact with the floor. L is equal to 1.7 meters. The radius of the wheel is 0.6 meters. The mass of AB, which is the rod, is 20 kilograms. The mass of the wheel is 50 kilograms. And again, theta is equal to 72 degrees. Not kinematics again. You never escape it. So doing these problems, we can take a look at only A, which is limited to moving only in the J direction, so downward in the Y. That's my expectation. And I can say that velocity of B equals velocity of A plus velocity of B relative to A. So again, sort of the same thing as I'm used to. Velocity of B in the I direction equals minus VAJ, because I know, according to the coordinate I had in the previous slide, this is negative, this is positive, plus omega AB, the rotational rate of that rod, times L cos theta, B with respect to A, excuse me, this way, and then down. So negative in the J direction. So if I put in the terms, I get VA equals LAB, omega AB cos theta, omega AB equals VA LAB cos theta. And if I wanted velocity of G, it'll probably be somewhere in here, because I kind of know that it's kind of an instantaneous center, and this is sort of the instantaneous center of this rod, and it'll sort of go off in a normal direction here. At the two positions given, I have T1, which is equal to 1/2 MAVAB1 squared, the translational kinetic energy, and I have the rotational kinetic energy, which is 1/2 IG omega 1 squared. I also have the change in terms of the height, V1, which is MABG, R, which is the radius, plus L sine theta 1. So it's climbing up here and then climbing up here. At position 2, it's at the bottom of that swing. There's the datum that I'm going to define, and I can say that it's going to be offset by a distance 1/2 MABGR. And I can sort of do all the calculations. It's going to, you can sort of do it yourself, but that's the geometry. You've got VG2 squared and omega 2 squared. It starts from rest, and you know you can calculate omega 2 and VG2 based on this. And you end up with one in terms of the other. T1 is equal to 0 joules. T2 is MABL squared, 6L squared minus R squared VA2 squared. Substituting in all the terms, putting everything together, you have a mess of terms here, but you have all of these MABs here. You can sort of substitute all of those, or pull those out. You get rad 3 over L, square root of G, L squared minus R squared, R plus L sine theta 1. So you end up just substituting in terms and equals 7.55 meters per second. This is kind of an interesting problem for no other reason than to just go through sort of a very complex geometry and sort of convince yourself that this makes sense. You can try it out, and I certainly do encourage you to do so. And again, with a lot of these examples, the math is all worked out here for you. The idea is that you do it on your own and try and make sure that you follow along. If the angular speed is omega-2 after displacing a distance d from release, what is the work done by friction? So I have an inner and an outer radius given to me. I have, again, x, which is up the ramp, y, which is normal to the ramp, and my positive momentum is counterclockwise. Theta is the angle of the ramp, and it's attached by this green cord. Mass of the spool is given as 30 kilograms. The inner radius is 20 centimeters. The outer radius is 30 centimeters. And the radius of gyration, again, a really important concept, 23 centimeters. The distance that this thing travels down is 2.3 meters. Omega-2 is equal to 1.34 rads per second, and theta is equal to 24 degrees. So we need to define the beginning and end positions. So at the beginning, we've got sort of a force pulling up. We've got friction force. We've got normal force. We've got weight and all of this. O is the point of contact, or is the instantaneous center of zero rotation or velocity, excuse me. Point in contact to the ramp is moving up the incline, and so it's counterclockwise rotation. Friction is acting in the opposite sense. So if it's traveling a distance d, goes from position 1 to position 2, and as it moves to 1 to 2, it's going to displace. So we know T1 plus V1 plus work 1 to 2 equals T2 plus V2. I'm just going to use, and I strongly recommend in all of these problems that you do this, that the non-conservative forces are going to be associated with work. Everything else, conservative forces, are potential energy. T is equal to 1/2 omega-1 squared. T2 is equal to 1/2 omega-2 squared. I naught, about O, is m kg squared plus r inner squared. Remember that this is a radius of gyration, so it's not 1/2 mr squared or anything like that. It's m kg squared. R inner squared is the distance from G to that point right here. And so that's why you do the R inner squared. B1 equals 0, B2 equals minus mgd sine theta. So it's moved down a distance d, but it's moved down a distance d sine theta in terms of vertical height. Omega-1 is equal to 0 rads per second. Omega-2 is equal to 1.34 rads per second. Work 1 to 2 then is just going to be the difference. So 1/2 mass, or 1/2 IO, omega-2 squared minus the change in height, and the work done is going to be minus 272.8 joules. Now the nice thing about this result is I know immediately that kind of makes sense. Friction always opposes motion, and it's always something that's going to work against me. And so if I get something that's sort of done there, I get a result from this. That's a good rolling problem, and the approach is standard. Just follow the steps. But as you go through these problems, try them on your own. Again, it's really kind of useful to do that and see what you come up with. Thank you very much, and we'll talk again.